to HitcHikers TV. This video lesson could be utilized as a supplemental instruction material to help students understand about plate tectonics theory. Copyright disclaimer: under Section 107 of the Copyright Act 1976, allowance is made for fair use for purposes such as criticism, commenting, news reporting, teaching, scholarship, and research. Fair use is a use permitted by copyright statute that might otherwise be infringing. Non-profit, educational, or personal use tips the balance in favor of fair use. This is for educational or teaching purposes. Come along and explore with HitcHikers TV. Let's learn about plate tectonics theory. First, let's define what is a theory. Theory is a supposition or a system of ideas intended to explain something, especially one based on general principles independent of the thing to be explained. Or a plausible or scientifically acceptable general principle or body of principles offered to explain phenomena according to Merriam-Webster Dictionary.
Yeah, boy!
So, what is plate tectonics theory? The theory of plate tectonics. The basic theory of plate tectonics is that along seafloor spreading zones, the continents are separating from one another. As they spread apart, magma comes to the surface and becomes new continental crust. As the tectonic plates move away from spreading zones, they collide with one another. As Britannica.com defines it as plate tectonics, a theory dealing with the dynamics of Earth's outer shell, the lithosphere, that revolutionized Earth sciences by providing a uniform context for understanding mountain building processes, volcanoes, and earthquakes, as well as the evolution of Earth's surface and reconstructing its past continents and oceans. In 1977, after decades of tediously collecting and mapping ocean sonar data, scientists began to see a fairly accurate picture of the seafloor emerge. The Tharp-Keesin map illustrated the geological features that characterize the seafloor and became a crucial factor in the acceptance of the theories of plate tectonics and continental drift. Today, these theories serve as the foundation upon which we understand the geologic processes that shape the Earth. In much the same way that geographic borders have separated, collided, and been redrawn throughout human history, tectonic plate boundaries have diverged, converged, and reshaped the Earth throughout its geologic history. Today, science has shown that the surface of the Earth is in a constant state of change. We are able to observe and measure mountains rising and eroding, oceans expanding and shrinking, volcanoes erupting, and earthquakes striking. Before the Tharp-Keesin map of the seafloor was published in 1977, scientists had little understanding of the geological features that characterized the seafloor, especially on a global scale. The data and observations represented by the Tharp-Keesin map became crucial factors in the acceptance of the theories of plate tectonics and continental drift. The theory of plate tectonics states that the Earth's solid outer crust, the lithosphere, is separated into plates that move over the asthenosphere, the molten upper portion of the mantle. Oceanic and continental plates come together, spread apart, and interact at boundaries all over the planet. Each type of plate boundary generates distinct geologic processes and landforms. At divergent boundaries, plates separate, forming a narrow rift valley. Here, geysers spurt superheated water, and magma, or molten rock, rises from the mantle and solidifies into basalt, forming new crust. Thus, at divergent boundaries, oceanic crust is created. The mid-ocean ridge, the Earth's longest mountain range, is a 65,000 kilometers, 40,390 miles, long and 1,500 kilometers, 932 miles, wide divergent boundary. In Iceland, one of the most geologically active locations on Earth, The divergence of the North American and Eurasian plates along the Mid-Atlantic Ridge can be observed as the ridge rises above sea level. At convergent boundaries, plates collide with one another. The collision buckles the edge of one or both plates, creating a mountain range or subducting one of the plates under the other, creating a deep seafloor trench. At convergent boundaries, continental crust is created and oceanic crust is destroyed as it subducts, melts, and becomes magma. Convergent plate movement also creates earthquakes and often forms chains of volcanoes. The highest mountain range above sea level, the Himalayas, was formed 55 million years ago when the Eurasian and Indo-Australian continental plates converged. The Mediterranean island of Cyprus formed at a convergent boundary between the African and Eurasian plates. Hardened mounds of lava, called pillow lavas, were once on the bottom of the ocean where this convergence occurred, but have been pushed up and are now visible at the surface. According to J. Brendan Murphy and all other contributors, the professors of geology, St. Francis Xavier University, Nova Scotia, Canada. As written in Britannica.com, plate tectonics theory deals with the dynamics of Earth's outer shell, the lithosphere, that revolutionized Earth sciences by providing a uniform context for understanding mountain building processes, volcanoes, and earthquakes, as well as the evolution of Earth's surface and reconstructing its past continents and oceans. The concept of plate tectonics was formulated in the 1960s. According to the theory, Earth has a rigid outer layer, known as the lithosphere, which is typically about 100 kilometers, 60 miles, thick and overlays a plastic, moldable, partially molten, layer called the asthenosphere. The lithosphere is broken up into 7 very large continental and ocean-sized plates, 6 or 7 medium-sized regional plates, and several small ones. These plates move relative to each other, typically at rates of 5 to 10 centimeters, 2 to 4 inches, per year, and interact along their boundaries, where they converge, diverge, or slip past one another. Such interactions are thought to be responsible for most of Earth's seismic and volcanic activity, although earthquakes and volcanoes can occur in plate interiors. Plate motions cause mountains to rise where plates push together, or converge, and continents to fracture and oceans to form where plates pull apart, or diverge. The continents are embedded in the plates and drift passively with them, which over millions of years results in significant changes in Earth's geography. The theory of plate tectonics is based on a broad synthesis of geologic and geophysical data. It is now almost universally accepted, and its adoption represents a true scientific revolution, analogous in its consequences to quantum mechanics in physics or the discovery of the genetic code in biology. Incorporating the much older idea of continental drift, as well as the concept of seafloor spreading, the theory of plate tectonics has provided an overarching framework in which to describe the past geography of continents and oceans, the processes controlling creation and destruction of landforms, and the evolution of Earth's crust, atmosphere, biosphere, hydrosphere, and climates. During the late 20th and early 21st centuries, it became apparent that plate tectonic processes profoundly influence the composition of Earth's atmosphere and oceans, serve as a prime cause of long-term climate change, and make significant contributions to the chemical and physical environment in which life evolves. In essence, plate tectonic theory is elegantly simple. Earth's surface layer, 50 to 100 kilometers, 30 to 60 miles, thick, is rigid and is composed of a set of large and small plates. Together, these plates constitute the lithosphere, from the Greek lithos, meaning rock. The lithosphere rests on and slides over an underlying partially molten, and thus weaker but generally denser, layer of plastic partially molten rock known as the asthenosphere, from the Greek asthenos, meaning weak. Plate movement is possible because the lithosphere-asthenosphere boundary is a zone of detachment. As the lithospheric plates move across Earth's surface, driven by forces as yet not fully understood, they interact along their boundaries, diverging, converging, or slipping past each other. While the interiors of the plates are presumed to remain essentially undeformed, plate boundaries are the sites of many of the principal processes that shape the terrestrial surface, including earthquakes, volcanism, and orogenic, that is, formation of mountain ranges. Past plate movements. Plate tectonics involves the movements of Earth's lithospheric plates relative to one another over the planet's weak asthenosphere. This activity changes the positions of all plates with respect to Earth's spin axis and the equator. To determine the true geographic positions of the plates in the past, investigators have to define their motions, not only relative to each other but also relative to this independent frame of reference. Hotspots, as classically interpreted, provide an example of such a reference frame, assuming they are the sources of plumes that originate within the deep mantle and have relatively fixed positions over time. If this assumption is valid, the motion of the lithosphere above these plumes can be deduced. The hotspot island chains serve this purpose, their trends providing the direction of motion of a plate. The speed of the plate can be inferred from the increase in age of the volcanoes along the chain relative to the distance between the islands. Earth scientists are able to accurately reconstruct the positions and movements of plates for the past 150 million to 200 million years because they have the oceanic crust record to provide them with plate speeds and direction of movement. However, since older oceanic crust is continuously consumed to make room for new crust, this kind of evidence is not available for earlier intervals of geologic time, making it necessary for investigators to turn to other, less precise techniques. In 1858, French geographer Antonio Snider Pellegrini proposed that identical fossil plants in North American and European coal deposits could be explained if the two continents had formerly been connected. He suggested that the biblical flood was due to the fragmentation of this continent, which was torn apart to restore the balance of a lopsided Earth. In the late 19th century, the Austrian geologist Eduard Suess proposed that large ancient continents had been composed of several of the present-day smaller ones. According to this hypothesis, portions of a single enormous southern continent designated Gondwana, or Gondwanaland, foundered to create the Atlantic and Indian Oceans. Such sunken lands, along with vanished land bridges, were frequently invoked in the late 1800s to explain sediment sources apparently present in the ocean and to account for floral and faunal connections between continents. These explanations remained popular until the 1950s and stimulated belief in the ancient submerged continent of Atlantis. In 1908, American geologist Frank B. Taylor postulated that the arcuate, bow-shaped, mountain belts of Asia and Europe resulted from the creep of the continents toward the equator. His analysis of tectonic features foreshadowed in many ways modern thought regarding plate collisions. Alfred Wegener and the concept of continental drift. In 1912, German meteorologist Alfred Wegener, impressed by the similarity of the geography of the Atlantic coastlines, explicitly presented the concept of continental drift. Though plate tectonics is by no means synonymous with continental drift, the term encompasses this idea and derives much of its impact from it. Wegener came to consider the existence of a single supercontinent from about 350 million to 245 million years ago, during the late Paleozoic era and early Mesozoic era, and named it Pangaea, meaning all lands. He searched the geologic and paleontological literature for evidence supporting the continuity of geologic features across the Indian and Atlantic Oceans during that time period, which he assumed had formed during the Mesozoic era, about 252 million to 66 million years ago. He presented the idea of continental drift and some of the supporting evidence in a lecture in 1912, followed by his major published work, The Origin of Continents and Oceans, 1915. evidence supporting the hypothesis. The strikingly similar Paleozoic sedimentary sequences on all southern continents and also in India are an example of evidence that supports continental drift. This diagnostic sequence consists of glacial deposits called tillites, followed by sandstones and finally coal measures, typical of warm moist climates. An attempt to explain this sequence in a world of fixed continents presents insurmountable problems. Placed on a reconstruction of Gondwana, however, the tillites mark two ice ages that occurred during the drift of this continent across the South Pole from its initial position north of Libya about 500 million years ago and its final departure from southern Australia 250 million years later. About this time, Gondwana collided with Laurentia, the precursor to the North American continent, which was one of the major collisional events that produced Pangaea. Both ice ages resulted in glacial deposits in the southern Sahara during the Silurian period, 443.8 million to 419.2 million years ago, and in southern South America, South Africa, India, and Australia from 382.7 million to 251.9 million years ago, spanning the latter part of the Devonian, as well as the Carboniferous and the Permian. At each location, the tillites were subsequently covered by desert sands of the subtropics and these in turn by coal measures, indicating that the region had arrived near the Paleo-equator. During the 1950s and 1960s, isotopic dating of rocks showed that the crystalline massifs of Precambrian age, from about 4.6 billion to 541 million years ago, found on opposite sides of the South Atlantic did indeed closely correspond in age and composition, as Wegener had surmised. It is now evident that they originated as a single assemblage of Precambrian continental nuclei later torn apart by the fragmentation of Pangaea. By the 1960s, although evidence supporting continental drift had strengthened substantially, many scientists were claiming that the shape of the coastlines should be more sensitive to coastal erosion and changes in sea level and are unlikely to maintain their shape over hundreds of millions of years. Therefore, they argued, the supposed fit of the continents flanking the Atlantic Ocean is fortuitous. In 1964, however, those arguments were laid to rest. A computer analysis by Sir Edward Bullard showed an impressive fit of these continents at the 1,000 meter, 3,300 foot, depth contour, which strongly supported the notion that Africa and South America were once joined together. A match at this depth is highly significant and is a better approximation of the edge of the continents than the present shoreline. With this reconstruction of the continents, the structures and stratigraphic sequences of Paleozoic mountain ranges in eastern North America and northwestern Europe can be matched in detail in the manner envisaged by Wegener. Ironically, the final vindication of Wegener's hypothesis came from the field of geophysics, the subject used by Jeffreys to discredit the original concept. The ancient Greeks realized that some rocks are strongly magnetized, and the Chinese invented the magnetic compass in the 13th century. In the 19th century, geologists recognized that many rocks preserve the imprint of Earth's magnetic field as it was at the time of their formation. The study and measurement of Earth's ancient magnetic field and the remnant magnetism in rocks is called paleomagnetism. Iron-rich volcanic rocks, such as basalt, contain minerals that are good recorders of remnant magnetism, and some sediments also align their magnetic particles with Earth's field at the time of deposition. These minerals behave like fossil compasses that indicate, like any magnet suspended in Earth's field, the direction to the magnetic pole and the latitude of their origin at the time the minerals were crystallized or deposited. During the 1950s, paleomagnetic studies, notably those of Stanley K. Runcorn and his co-workers in England, showed that in the late Paleozoic era the North Magnetic Pole as reconstructed from European data seems to have wandered from a Precambrian position near Hawaii to its present location in the Arctic Ocean by way of Japan. This could be explained by the migration of the magnetic pole itself, that is, polar wandering, by the migration of Europe relative to a fixed pole, that is, continental drift, or by a combination of these processes. When paleomagnetic data from other continents was obtained, each continent yielded different results. The possibility that they might reflect true wandering of the poles was discarded, because it would imply separate wanderings of many magnetic poles over the same period. However, these different paths could be reconciled into the same path by joining the continents in the manner and at the time suggested by Wegener. In other words, this analysis implied that the poles' geographic variations could be explained by the wandering of the continents. These geographic variations are called apparent polar wander paths, and they are thought to be artifacts of continental drift. Impressed by this result, Runcorn became the first of a new generation of geologists and geophysicists to accept continental drift as a proposition worthy of careful testing. Since then, more sophisticated paleomagnetic techniques have provided both strong supporting evidence for continental drift and a major tool for reconstructing the geography and geology of the past. After World War II, rapid advances were made in the study of the relief, geology, and geophysics of the ocean basins. Largely because of the efforts of American oceanographer Bruce C. Heezen, American geologist Henry W. Menard, and American oceanic cartographer Marie Tharp, ocean basins, which constitute more than two-thirds of Earth's surface, became well enough known to permit serious geologic analysis. The studies revealed three very important types of features present on the ocean floor. The first type appears as broad bulges in the oceanic crust known as ocean ridges. The second set of features was revealed as deep and narrow linear troughs known as oceanic trenches. The third type occurred in seismically active fracture zones and became known as transform faults. Discovery of ocean basin features systematic measurements of ocean depth conducted during the middle of the 20th century, and the three-dimensional relief maps that were produced from these surveys revealed broad, relatively elevated oceanic ridges that form an interconnected network about 65,000 kilometers, 40,000 miles, in length and nearly girdle the globe. Ocean ridges have elevations that typically rise 2 to 3 kilometers, 1.2 to 1.9 miles, above the surrounding seafloor, and widths that range from a few hundred to more than 1,000 kilometers, 600 miles. Their crests tend to be rugged and are often endowed with a rift valley at their summit where fresh lava, high heat flow, and shallow earthquakes typical of extensional environments, areas where the crust is stretched rather than compressed, are found. These surveys also revealed long, narrow depressions, oceanic trenches that virtually ring the Pacific Ocean. A few also occur in the northeastern part of the Indian Ocean, and some small ones are found in the central Atlantic Ocean that encircle the Caribbean plate. Elsewhere they are absent. In contrast to ocean ridges, trenches have low heat flow, are often, but not always, filled with thick sediments, and lie at the upper edge of the weighted-even zone of compressive earthquakes. Trenches may border continents, as in the case of Western Central and South America, or may occur in mid-ocean, as, for example, in the southwestern Pacific. Offsets of up to several hundred kilometers along oceanic ridges and, more rarely, trenches were also recognized, and these fracture zones, later termed transform faults, were described as transverse features consisting of linear ridges and troughs. In oceanic domains, these faults were found to occur approximately perpendicular to the ridge crest, continue as fracture zones that extend over long distances, and terminate abruptly against continental margins. They are not sites of volcanism, and their seismic activity is restricted to the area between offset ridge crests, where earthquakes indicating horizontal slip are common. Hess's seafloor spreading model. The existence of these three types of large, striking seafloor features demanded a global rather than local tectonic explanation. The first comprehensive attempt at such an explanation was made by Harry H. Hess of the United States in a widely circulated manuscript written in 1960 but not formally published for several years. In this paper, Hess, drawing on Holmes's model of convective flow in the mantle, suggested that the oceanic ridges were the surface expressions of rising and diverging convective mantle flow, while trenches and weighted Ivanov zones, with their associated island arcs, marked descending limbs. At the ridge crests, new oceanic crust would be generated and then carried away laterally to cool, subside, and finally be destroyed in the nearest trenches. Consequently, the age of the oceanic crust should increase with distance away from the ridge crests, and, because recycling was its ultimate fate, very old oceanic crust would not be preserved anywhere. This model explained why rocks older than 200 million years had never been encountered in the oceans, whereas the continents preserve rocks almost 4 billion years old. Hess's model was later dubbed seafloor spreading by the American oceanographer Robert S. Dietz. Confirmation of the production of oceanic crust at ridge crests and its subsequent lateral transfer came from an ingenious analysis of transform faults by Canadian geophysicist J. Tuzo Wilson. Wilson argued that the offset between two ridge crest segments is present at the outset of seafloor spreading. As each ridge segment generates new crust that moves laterally away from the ridge, the crustal slabs move in opposite directions along that part of the fracture zone that lies between the crests. In the fracture zones beyond the crests, adjacent portions of crust move in parallel, and are therefore aseismic, that is, do not have earthquakes, and are eventually consumed in a subduction zone. Wilson called this a transform fault and noted that on such a fault the seismicity should be confined to the part between ridge crests, a prediction that was subsequently confirmed by an American seismologist, Lynn R. Sykes. After decades of controversy, the concept of continental drift was finally accepted by the majority of Western scientists as a consequence of plate tectonics. Sir Harold Jeffreys continued his lifelong rejection of continental drift on grounds that his estimates of the properties of the mantle indicated the impossibility of plate movements. He did not, in general, consider the mounting geophysical and geologic arguments that supported the concept of Earth's having a mobile outer shell. Russian scientists, most notably Vladimir Vladimirovich Belousov, continued to advocate a model of Earth with stationary continents dominated by vertical motions. The model, however, only vaguely defined the forces supposedly responsible for the motions. In later years, Russian geologists came to regard plate tectonics as an attractive theory and a viable alternative to the concepts of Belousov and his followers. In 1958, the Australian geologist S. Warren Carey proposed a rival model, known as the expanding Earth model. Carey accepted the existence and early Mesozoic breakup of Pangaea and the subsequent dispersal of its fragments and formation of new ocean basins, but he attributed it all to the expansion of Earth, the planet presumably having had a much smaller diameter in the late Paleozoic era. In his view, the continents represented the pre-expansion crust, and the enlarged surface was to be entirely accommodated within the oceans. This model accounted for a spreading ocean floor and for the young age of the oceanic crust. However, it failed to deal adequately with the evidence for subduction and compression. Carey's model also did not explain why the process should not have started until some 4 billion years after Earth was formed, and it lacked a reasonable mechanism for so large an expansion. Finally, it disregarded the evidence for continental drift before the existence of Pangaea.